This is going to be a brief introduction to screeners. So what exactly is a screener? In simple terms, it's a brief assessment tool designed with the specific aim of predicting a gold standard diagnosis of a particular condition. So it's this process where the essence of diagnostics is distilled into a rapid, efficient tool. Unlike extensive diagnostic tests, screeners are characterized by their brevity and precision. Now, what does it mean when we say a screener is continuously scaled? It means that the screener is often self-reported. And this allows the person to place themselves on a spectrum or scale relating to a particular condition or symptom. This continuity in scaling offers a nuanced and individualized perspective, enabling us to pinpoint where a person might fall on a diagnostic spectrum. But how do we ensure accuracy? And this is where the gold standard, or the GS diagnosis, comes into play. This represents the truth criterion. This is like a yardstick by which all else is measured. It's the compass that guides our understanding, and it's assumed to exhibit near perfect reliability. When we talk about a strong validity coefficient in a screener, we're referring to how well the screener predicts this gold standard diagnosis. A critical part of developing a screener is determining a cutoff value. So imagine this cutoff value as a line in the sand. Scores falling above this line are likely to be diagnosed with the condition assessed by the gold standard. On the other hand, scores below this cut point indicate a lesser likelihood of being diagnosed with that condition. This binary division might seem simple, but choosing the right cutoff point is complex. It's a decision that carries significant weight, and this impacts both validity and the utility of the screener. So let's look at all the possible combinations. With diagnostic evaluation, we're focusing specifically on the intricate relationships between screener results and gold standard diagnoses. This is where the art and science of diagnostics come together. It weaves this complex tapestry that defines the accuracy, efficiency, and reliability of our assessments. Let's first ground ourselves in the fundamental building blocks of this matrix. Let's look at the positive screen. This refers to the cases where the screener indicates the presence of a specific diagnosis or condition. Our negative screen, this is referring to the instances where the screener does not detect the presence of a particular condition. The gold standard diagnosis present, this is the diagnosis or of our true measure, and this confirms the presence of the condition. This is at the present. When it's absent, we're saying that this confirms the absence of a condition. With these four core elements, we find ourselves in a realm of possibilities and combinations that give us rise to four primary scenarios. We have a true positive, which is A, the top left. This is when you have a positive screen and the gold standard diagnosis is present. This is the ideal situation where the screener correctly identifies the presence of a condition and the gold standard diagnosis confirms it. It's a match. It's a win-win. If you look at scenario B, right to the right side of it, this is a positive screen, but from the gold standard diagnosis, it's absent. This means that the screener mistakenly identifies the presence of a condition, but the gold standard diagnosis negates it. This is known as a false alarm. The false negative, in this scenario, the screener fails to detect the presence of a condition that is confirmed by the gold standard diagnosis. This is the missed opportunity. And then lastly, we have our true negative. This scenario is where both the screener and the gold standard diagnosis correctly identify the absence of a condition. It's another match, which is a successful confirmation of the absence. And I want to delve deeper into these statistical measures and concepts from that table. And this is paramount in the field of diagnostics. These concepts are instrumental in interpreting and assessing the performance of a screening tool, and they hold significant implications for practical applications. So if we look at the positive predictive value, mathematically, this is A divided by A plus B. And if we go back to the table, this is going to be the true positives divided by the sum of the true positives and false positives, which is the same thing as saying the true positives divided by positive screens. This is known as the success ratio, and PPV describes the proportion of positive screens that result in the correct gold standard diagnosis. A high PPV means that when the screener detects the presence of a condition, it's likely to be confirmed by the gold standard diagnosis. This value informs us about the credibility of positive results, and it can directly influence treatment decisions. A low PPV could lead to unnecessary interventions or anxiety, while high PPV increases increases confidence in the screener's ability to detect true positives. We also have a negative predictive value, the NPV. This is also known as the negative success ratio, and it describes the proportion of negative screens resulting in the correct gold standard diagnosis. A high negative predictive value indicates that when the screener does not detect a condition, it's highly likely to be absent according to the gold standard diagnosis. This impacts decisions related to further testing or exclusion of treatment. It plays a crucial role in minimizing unnecessary tests, lowering costs, and reducing potential risk to the patient. We also have the sensitivity and specificity scales. So if we're looking at this, let's try to look at this from a column perspective. Sensitivity is A divided by the sum of A and D, which means that this is the true positives divided by the gold standard true cases. And specificity is going to be the true negatives divided by the false cases. So sensitivity, this measures the proportion of true cases correctly identified as positive by the screener. A highly sensitive test indicates that the screener is highly capable of identifying true positives, minimizing the risk of missing individuals with the condition. Essentially, in early detection and preventative care, low sensitivity could have serious consequences in critical conditions, leading to misdiagnoses. Whereas for specificity, this is the proportion of false cases correctly identified as negative by the screener. High specificity means low false positive rates, thus reducing unnecessary interventions for individuals without the condition. It ensures efficient resource allocation and minimizes potential harms associated with overdiagnosis. Let's go over some more diagnostics. We have the false negative rate, which mathematically is 1 minus the sensitivity, which is the same thing as saying D over the sum of A and D. It's defined as the proportion of true cases that are incorrectly identified as negative by the screener. A high false negative rate means that individuals with the condition are being missed, leading to potential treatment delays. It's critical in high stakes scenarios where misdiagnoses may lead to severe consequences. We also have the false positive rate, which mathematically is 1 minus the specificity value, which is the same thing as saying B divided by the sum of B and C. And this is the proportion of false cases that are incorrectly identified as positive by the screener. A high false positive rate may lead to unnecessary further testing or treatment, causing anxiety and additional costs. Balancing specificity to minimize this rate is key to patient safety and health economics. We also have the selection ratio, and mathematically, this is the sum of A and B divided by the sum of A, B, C, and D. The selection ratio refers to the proportion of positive screens, both true and false. The selection ratio can be manipulated by adjusting the cutoff value of the screener, and this influences both the positive predictive value and the negative predictive value. Understanding and controlling selection ratio allows for the optimization of a screener according to specific needs or population. We also have the base rate. Mathematically, this is defined as the sum of A and D divided by the sum of A, B, C, and D. And the base rate represents the proportion of positive gold standard diagnoses in the screened population. A low base rate for events such as suicide or homicide makes prediction challenging due to rarity. There's some implications. Awareness of the base rate is vital for understanding the context in which a screener operates, and this informs its design, implementation, and interpretation. Now, I want to expand on the concept of base rates, specifically focusing on the challenges associated with low base rates phenomena. This is the influence of local base rates on the optimal cutoff for diagnosis and the dependency on the criteria used for making the diagnosis, such as the DSM. So base rates, again, represent the prevalence or proportion of a condition or phenomenon within a specific population. This is critical because it provides a context for interpreting the results of screening or diagnostic tests. We have the low base rate phenomenon, which refers to the conditions or events that occur rarely within a specific population. These examples include rare diseases, criminal behaviors like homicide, or highly specialized talents. There are several complexities and challenges associated with low base rates. There's prediction difficulty, which means that rare events are inherently hard to predict accurately. The fewer occurrences within a population, the more challenging it becomes to establish a reliable pattern. There's false positives. In low base rate conditions, false positives incorrectly identify the presence of a condition and can easily outnumber true positives. And this leads to a paradox where a positive test result might still mean a low low probability of the condition being present. We also have resource allocation to think about, because attempting to identify rare conditions might lead to over-testing and unnecessary interventions, thus consuming valuable resources that might be more effectively used elsewhere. We also have ethical considerations, because high false positive rates could lead to unnecessary stress and stigmatization of individuals, and that raises ethical concerns. Let's talk about the optimal cutoff depending on the local base rate. The optimal cutoff point for a screener or a diagnostic tool depends on the local base rate, or the prevalence of the condition within the specific community or group that's being examined. And here's why. The cutoff must be set to achieve an appropriate balance between sensitivity, which is detecting true positives, and specificity, avoiding false positives. This balance may differ based on the base rate. The base rate directly influences the positive predictive value and the negative predictive value. A higher base rate will generally increase the PPV, while a lower base rate may decrease it. Different populations may have different base rates for the same condition, and this necessitates customization of cutoff values to align with local needs and realities. We have to also have economic considerations in mind, because optimal cutoff points also need to consider cost effectiveness, particularly in low base rate conditions where extensive screening might lead to many false positives. And now, the dependency of diagnostic criteria, i.e. the DSM. The choice of criteria for making a diagnosis is pivotal and influences all aspects of the diagnostic process, including the base rate. We have standardization and consistency. So tools like the DSM provide standardized criteria for diagnosing mental health disorders, ensuring consistency across different settings. It has an influence on the base rate, because different criteria may identify different numbers of individuals with the condition, thus influencing the base rate. More inclusive criteria might increase the base rate, while more stringent criteria may decrease it. And there's an interplay with cutoff values, because the alignment of diagnostic criteria with the screener's cutoff values ensures that the screening process is truly reflective of the condition as defined by the prevailing standards. We also have to have this evolving understanding, because as scientific understanding evolves, diagnostic criteria may change, and this influences base rates and necessitates adjustments in screening practices. I want to go through an example of how base rates influence the PPV and the NPV. Let's say we have a total population of 1,000 people, and let's say our total true cases where the disease is present, we're going to look at A plus D, and that's going to be 300. Our false cases where the disease is absent is going to be 700, that's B plus C. Our base rate is A plus D divided by the sum of A, B, C, and D. And that's going to equal 300 divided by 1,000, meaning everyone. And that's going to give us 0.3 as our base rate. Sensitivity and specificity assume that they're fixed at reasonable values. They represent the effectiveness of this test in identifying the true positives and true negatives. So let's explore how this base rate is going to influence PPV and NPV. So with a base rate of 0.3, the PPV will reflect how well the test performs in a population where 30% of the individuals actually have the condition. The choice of sensitivity will further influence the PPV in this context. A higher base rate would usually lead to a lower NPV, as more true cases and potentially more false negatives exist in the population. And with our given base rate of 0.3, the NPV will be influenced by how well the test can accurately identify the absence of the condition among the 70% who do not have it. In achieving high PPV and NPV simultaneously, this can be challenging, particularly in low or high base rate scenarios. So the choice of cutoff values for positive and negative screens will need to be calibrated according to the base rate, the sensitivity, and specificity to achieve an optimal balance between PPV and NPV. Now, let's take this understanding to a more profound level by considering two distinct examples. So this next one, we're going to have a base rate of 0.05, meaning A plus D divided by the total in the population for this study is 0.05. Sensitivity and specificity are fixed at the same values, indicating that our cutoff didn't change. So in this scenario, we're dealing with a low base rate phenomenon, representing only 5% of the total population. With such a low base rate, a positive result on the screener is more likely to be a false positive, as true cases are rare, and consequently, PPV may decrease. For NPV, since the base rate is low, most of the population do not have the condition. Thus, a negative result on the screener is more likely to be a true negative, leading to a higher NPV. In the second example, we have a base rate of 0.01, where sensitivity and specificity are fixed at the same values, meaning our cutoff didn't change again. This example takes us to an even lower base rate of 1%, further emphasizing the challenges of low base rate phenomena. The likelihood of true positive cases becomes even rarer in this scenario. Therefore, PPV would likely decrease further as as false positives become more common relative to true positives. And for negative predictive value, again, with such a low base rate, the probability that a negative screen result is a true negative increases, leading to an even higher NPV. These two examples illuminate the critical importance of understanding and considering base rates in the diagnostic process. They show the impact on PPV and NPV and how varying base rates, even with fixed sensitivity and specificity, can profoundly alter the PPV and NPV. It also shows how low base rate events like rare diseases can be particularly challenging to predict accurately, and that affects both clinical decision-making and policy formulation. And the necessity to carefully consider local base rates and potentially tailor screening cutoff values and procedures accordingly to optimize predictive values. Through the three distinct examples that we just shown, we've seen how changing the base rate affects our ability to identify individuals with the gold standard positive diagnosis. As the base rate decreases, so does the proportion of positive screens who are actually gold standard positive. This is a direct and sometimes troubling consequence of low base rate phenomena. One low base rate challenge is that a positive screen does not equal a positive diagnosis. This is a critical takeaway in that with low base rate phenomena, a positive screen does not necessarily translate to a positive diagnosis, and the rarer the condition, the more complex our task becomes. We've yet to discuss the nuanced procedures for determining optimal cutoff values for the screener, and this is an essential aspect of the process that influences selection ratios, sensitivity, specificity, and ultimately the PPV and NPV. I want you to imagine you're trying to find a rare gem in a big pile of stones. If the gem is very rare, even if you have a tool that's good at finding gems, you might still end up with lots of regular stones that look like gems. It's your false positives. As the gem becomes even rare, your tool might be finding fewer real gems than more fake ones. You might need to look again and again, which means you're taking multiple screens in real life, or you got to come up with better rules for deciding what's a gem and what's not. That's your optimal cutoff values. This is a complex puzzle, and solving it can make a big difference in finding what you're looking for, whether it's a rare gem or a rare medical condition. I want to delve into an intriguing and practical strategy for tackling low base rate phenomena, which is called sequential screening. And it's a step-by-step approach to increase our ability to detect rare events, especially those with low base rates in the population. Let's start with the situation where our base rate in the population is 0.05. That's just 5% of the population presenting the condition we're screening for. In the initial screening, our positive predictive value is 0.30, meaning 30% of those screened positive actually have the condition. Now let's turn our attention to the individuals flagged as positives by the initial screening. These become the subjects for our follow-up screening. Here's the clever part. The base rate in this subset is now the PPV of the initial screen, which was 0.30. That's a significant increase from our starting base rate of 0.05. And then we have follow-up screening for the PPV. And that means conducting the follow-up screening on this subset yields an impressive PPV of 0.77, meaning we've increased our accuracy in identifying true positives. Sequential screening offers some distinct advantages, including efficiency, because by focusing on subsequent screenings on the subset of individuals who tested positive in the initial screening, resources can be used more effectively. This leads to increased accuracy because the apparent base rate increases dramatically in the targeted subgroup, leading to a higher positive predictive value in the follow-up screening. Also, flexibility. This approach can be tailored to different conditions and settings, and this allows for modifications based on the needs and constraints of a particular screening effort. Some important drawbacks to consider are screening tool constraints. It's essential to use a screening tool not subject to rehearsal or memory effects, as the same subjects undergo multiple screenings. You must be aware that false negatives from the initial screening are excluded from the pool, potentially leading to misdiagnoses. And also, the independence assumption. This method assumes that each screening represents an independent trial, a hypothesis that may not always hold true. Some ethical considerations is that informed consent should be obtained, and participants should be aware of the process and potential implications, including the risk of false positives and negatives. There's logistical challenges. Planning and conducting sequential screenings might be complex and resource intensive, and this requires careful planning and collaboration among various stakeholders. Cost effectiveness. The cost implications of sequential screening should be assessed to ensure that this approach is not only more accurate, but also cost effective compared to other methods. We also need to think about integrating with other strategies, because sequential screening could be part of a broader strategy, including public awareness, education, and collaboration with healthcare providers and different organizations. We have to think about ongoing monitoring and evaluation of the sequential screening process, because this is essential to ensure its effectiveness and to make sure necessary adjustments are made based on the results in changing circumstances. I need you to also consider comorbidity, because in many mental health conditions, comorbidity is a factor that may complicate sequential screening, and care must be taken to consider and account for this complexity. It can be a valuable method for detecting rare events in clinical psych, provided it's carefully planned and implemented, and you're considering all these potential drawbacks and challenges. And collaboration among researchers, clinicians, and other stakeholders, along with ongoing evaluation, will be the key to success for this approach. If successfully applied, it could lead to earlier detection and intervention for conditions like schizophrenia, for instance, something that's rare, and that'll potentially improve outcomes for many individuals. I want to take this moment to revisit and emphasize a key point we've been discussing, which is the influence of base rates on PPV and MPV. For PPV and rarity, PPV declines sharply as a condition becomes more rare, and that was seen with the lower base rate. This means that if the condition is very rare, even if your test shows a positive result, it's more likely to be a false positive. Let's take, for example, the initial screening with the base rate of 0.05. The base rate is the proportion of the population that actually has the condition you're testing for. In this example, with the base rate of 0.05, meaning 5% of the population has the condition, we'll assume that sensitivity and specificity are reasonably high. Why is this important? If a condition is rare, even a test that is usually accurate can produce more false positives. This is because the small number of true positive cases can be overshadowed by false positives. So you want to understand the relationship between your base rate and the PPV when planning how to screen for rare conditions, because it's going to inform your decision about what tests to use, how to interpret the results, and whether or not you need to use sequential or other specialized screening strategies. And lastly, I want to break down this example in a little bit of simpler terms to understand what's happening in the sequential screening process. So in the initial screening, you first conduct the test on the general population. You know that only 5% actually have the condition. That's 0.05. And your test positive predictive value is 30%. That's 0.30. This means that out of those you test positive, only 30% really have the condition. Now you focus only on those who tested positive in the initial screening. So you do this second screening. The base rate for this specific group is now 30%, 0.30, and that's because the PPV of the initial screen. We're going to calculate the true and false cases. So for the positive screen, the true cases, well, 30% have the condition, and the test sensitivity is 80%, which means it correctly identifies 80% of the true cases. So you get 0.3 times 0.8, which is 0.24 true positive cases. For false cases, 70% don't have the condition, and the test has a 10% false positive rate, meaning it wrongly identifies 10% of healthy people as having the condition. 0.7 times 0.1 is 0.07 false positive cases. In the resulting PPV, the positive predictive value is the true positives divided by the total positives. So here, this would be 0.24 divided by the sum of 0.24 and 0.07, which is going to give us 77%. For the negative screen, true cases, 30% of the condition, but the test misses 20%. 1 minus sensitivity, you'll get 0.3 times 0.2, which is equal to 0.06, and that's true negative cases. For false cases, well, 70% don't have the condition, and the test correctly identifies 90% of them. So you get 0.7 times 0.9, which is equal to 0.63 false negative cases. The negative predictive value is the false negatives divided by the total negatives, which is 0.63 divided by 0.63 plus 0.06, which is 91%. So to conclude, this example demonstrates that by conducting a second screening on a specific subset of individuals, those who tested positive initially, you can significantly increase the accuracy of a test from 30% to 77% of positive cases. It's not just a theoretical exercise. It's a practical way to improve the effectiveness of screening for rare conditions. By understanding how these numbers work, you as a future healthcare provider can create more targeted and successful screening strategies. Simply put, by screening those who already tested positive, you can filter out many false cases and get a clear picture of who really has the condition. It's like double checking your work to make sure you're right, but using a method grounded in statistical analysis.